You know, when most people hear the word alcohol, their mind probably jumps straight to drinks, right?
Right.
Beer, wine, that sort of thing.
Yeah, that's the common association.
But here's something maybe surprising.
Yeah.
The actual world of organic alcohols is huge, way beyond just that one molecule.
Absolutely.
Like, did you know ethylene glycol, the stuff in antifreeze, that's an alcohol?
Mm.
Or methanol, sometimes called wood alcohol. That one can cause blindness if you ingest it.
Very dangerous, yes.
Even the isopropyl alcohol for cuts the stinging stuff,
Mm.
also an alcohol.
It's a whole family of compounds, really.
It really is an incredibly diverse chemical family. And today, that's what we're diving into.
Sounds good.
Our mission is to unpack how these molecules are classified, how chemists actually name them properly, and maybe most importantly, how they're made and transformed.
The reactions, yeah.
And we're pulling our insights from a fantastic guide, a chapter in Organic Chemistry for Dummies. It's great for turning complexity into something, clearer.
It is. And what's really fascinating here, I think, is just how central this functional group, the alcohol group, is. Not just in products, but in organic chemistry itself.
How so?
Well, think of them like molecular Lego bricks. They're super versatile. You can form them pretty easily, and you can just as easily convert them into tons of other important chemical groups.
Oh, okay.
So they're a cornerstone for making all sorts of things. Medicines, plastics, you name it.
Okay, let's unpack that a bit. We hear alcohol. We know the OH group is involved somehow.
Mm-hmm.
But what exactly defines it in chemistry terms?
Yeah.
Beyond just, cocktails or disinfectants.
You're right. So fundamentally, an alcohol is any organic molecule that has a hydroxyl, that's the OH group.
Okay.
And that OH group has to be bonded directly to a carbon atom that isn't part of an aromatic ring, like benzene.
Gotcha. So not just any OH group anywhere.
Exactly. Now, the classification part, that depends on the carbon that's holding the OH group.
How does that work?
It's about how many other carbon chains, chemists call them alkyl groups, are attached to that specific carbon. So if that carbon, the one bonded to the OH, is only attached to one other alkyl group, just one carbon chain, we call that a primary alcohol.
Or 1 degree.
Primary with one attachment. Makes sense.
Yep. If that same carbon is holding onto 2 other alkyl groups, it's secondary, 2 degrees.
Okay.
And, you guessed it, if it's attached to 3 other alkyl groups, it's tertiary, 3 degrees. It's all about that carbon's immediate neighbors, the carbon ones anyway.
So primary, secondary, tertiary. It's not just random labels, is it? This classification must, mean something for how they behave.
Oh, absolutely. That's the key insight. Understanding this classification is crucial because primary, secondary, and tertiary alcohols react very differently.
Okay.
Knowing the classification tells you a lot about what reactions it will or won't do. It's like knowing if a tool is a hammer or a screwdriver, different uses, different outcomes. It guides the whole process.
Right. It predicts reactivity. Okay, so we know what they are, how to classify them. Now, how do we give them their proper names? This always feels like a secret code. Hey, it can feel that way, but it's actually very systematic. It's a universal language, so chemists everywhere know exactly what molecule you're talking about.
So how do we crack it?
Well, it builds on the rules for naming basic carbon chains, the alkanes. There are basically 5 steps.
5 steps, okay.
First, find the longest continuous chain of carbon atoms that includes the carbon holding the OH group. That's your parent chain.
Longest chain with the OH. Got it.
Then you take the alkane name for that chain length, like ethane or propane, snip off the final E, and replace it with ol. That old ending screams alcohol.
So ethane becomes ethanol.
Exactly. That's the simple example. Step 2, number that parent chain.
Numbering. How?
You start numbering from the end that's closer to the hydroxyl group. The OH group gets the lowest possible number. It has priority.
Okay, lowest number for the OH.
Third step, identify any other groups attached to the main chain. These are called substituents. Name them.
Like methyl groups or ethyl groups.
Precisely. Fourth step, arrange those substituent names alphabetically and put them out front of the parent name.
Alphabetical order, okay.
And finally, step 5, you need to show where the hydroxyl group is. You put its number right before the parent name. Sometimes it's put right before the old suffix, but putting it before the parent name is very common.
All right, let's try an example. Maybe the one from the source material.
Good idea. Let's take a 3005-dimethyl-3-heptanol. Big name.
Whoa, okay. Break that down.
Right. So heptanol tells us the longest chain, including the OH, has 7 carbons. Heptane becomes heptanol.
7 carbons.
The 3 right before heptanol tells us the OH group is on the 3rd carbon of that 7-carbon chain.
Okay, position 3.
Then we look at the front. Dimethyl. That means there are 2 methyl groups, right? CH3 group.
Two methyls, where are they?
The numbers 3, 5 tell us. One methyl group is on carbon 3, the other is on carbon 5.
Ah, so the numbers locate everything.
Exactly. And we numbered the chain, probably from right to left in this case, to give that OH group on carbon 3 the lowest number, putting it all together. 3005-3 heptanol.
That is a mouthful, but yeah, following those steps, you can decode it. Or build the name yourself. It's logical.
It is. Precision is key in chemistry communication.
Okay, now for the really fun part, I think. How do we actually make these things? If you need an alcohol, how do you synthesize it? What are the main reactions?
Right, the creation process. Well, one major way is by adding water across carbon double bonds. We touched on this when we talked about alkenes. It's called hydration.
Hydration, adding water.
Okay. But here's where control comes in. There are different ways to do it. One method, oxymercuration-demercuration, usually gives you what's called the Markovnikov product.
Markovnikov. What does that mean again?
It means the OH group adds to the carbon of the double bond that already has more carbon substituents attached to it. Sort of a rich get richer situation for carbon attachments.
Okay, OH goes to the more substituted carbon.
But what if you want the opposite? What if you need the OH on the less substituted carbon?
Ah, there must be a way.
There is. That's hydroboration-oxidation. It gives the anti-Markovnikov product. The OH goes on the carbon with fewer carbon attachments.
So chemists have tools to put the OH group exactly where they want it on that original double bond. That's clear.
It's all about control and getting the specific molecule you need.
Okay, what else? You mentioned reduction earlier and some interesting tools. Pop guns and cannons?
Yeah, that's another major route. Reducing carbonyl compounds. Remember, a carbonyl is a C double bond O group.
CO, like in aldehydes and ketones.
Exactly. Aldehydes and ketones are prime candidates. We use reducing agents for this. One common one is sodium borohydride, NaBH₄.
Okay.
You can think of it as the reductive pop gun. It's strong enough to reduce the easier carbonyls, aldehydes, and ketones down to alcohols.
Pop gun for the easy targets. Got it. What about tougher ones?
For more stubborn carbonyls like esters and carboxylic acids, NaBH₄ isn't usually strong enough. You need the reductive cannon.
The cannon.
That's lithium aluminum hydride, LiAlH₄. Much more powerful. It can reduce esters and carboxylic acids, and it also reduces aldehydes and ketones.
Okay, so different strengths for different jobs. What kind of alcohols do you get?
Good question. If you reduce an aldehyde with other reagent, you always get a primary alcohol.
Aldehyde to primary alcohol.
If you reduce a ketone again with either reagent, you get a secondary alcohol.
Ketone to secondary alcohol. Makes sense.
But here's a key point. You cannot make tertiary alcohols this way by reduction of a carbonyl.
Oh, interesting. Why not?
Because you'd need to start with something that already has 3 carbons attached to the carbonyl carbon, and there's no simple carbonyl like that which reduces to a tertiary alcohol. Reduction adds hydrogens. It doesn't typically add carbon groups in this context.
Okay, so no tertiary alcohols from reduction. What about the esters and acids with the cannon, LiAlH₄?
Both esters and carboxylic acids, when reduced by LiAlH₄, give you primary alcohols.
Primary alcohols again. Okay, so reduction is great for primary and secondary, but not tertiary.
Exactly. And the choice of reagent matters, especially if you have, say, an ester and a ketone in the same molecule and only want to reduce the ketone, you'd use the pop gun, NaBH₄.
Right, selectivity.
Okay.
Oh, but what if you don't need a tertiary alcohol? Or what if you want to actually add more carbon atoms while making the alcohol? Reduction doesn't do that.
That's where the Grignard reaction comes in. It's a real superstar for making alcohols, especially tertiary ones, and for building bigger carbon skeletons.
The Grignard, I've heard of that one. Sounds important.
It's extremely useful. It involves reacting a special reagent, a Grignard reagent, with a carbonyl compound.
How do you make this Grignard reagent?
Surprisingly simple, actually. You take an alkyl halide, like methyl bromide or ethyl chloride, and react it with magnesium metal. The magnesium literally just inserts itself between the carbon and the halogen.
Magnesium squeezes in.
Okay. And what this does is it creates a molecule where the carbon atom bonded to the magnesium is very electron rich. It acts like a carbon with a negative charge, a carbanion, even though it's bonded to MgBr or MgCl.
So it's like a negatively charged carbon ready to attack.
Exactly. It's a very powerful nucleophile. It loves to attack the slightly positive carbon atom in a carbonyl group, CO.
Ah, the opposite charges attract.
Precisely. And the beauty is you form a new carbon-carbon bond in the process. You're adding the carbon part of the Grignard reagent to the carbonyl carbon.
So you build the molecule adding carbons.
Yes. And this lets you make all types of alcohols. If you react a Grignard reagent with formaldehyde, that's the simplest aldehyde with only H's attached to the CO, you get a primary alcohol after adding water in the workup step.
Grignard plus formaldehyde primary. Okay.
If you react it with any other aldehyde,
like acetaldehyde.
Yep, you get a secondary alcohol.
Grignard plus other aldehyde is secondary.
And if you react a Grignard reagent with a ketone,
let me guess. Tertiary alcohol.
You got it. Grignard plus a ketone gives you a tertiary alcohol. So if you need that tertiary alcohol, Grignard is often your go-to method.
Wow, okay. So reduction for primary, secondary, Grignard for all three, and for building bigger molecules. That's a powerful toolkit.
It really is fundamental to organic synthesis.
So we've seen how to make them. Now let's flip it. What can alcohols do? What can they become? You call them versatile building blocks.
Right, they're great starting points too. They can be transformed into many other functional groups, like molecular chameleons.
Okay, give me some examples.
Well, one common reaction is dehydration, losing water.
Dehydration sounds like it removes water.
Exactly. You treat the alcohol, often with a strong acid or a reagent like phosphorus oxychloride, POCl₃, and it eliminates water, the OH group, from one carbon and an H from an adjacent carbon to form an alkene, a carbon double bond.
Alcohol to alkene.
Then there's a classic way to make ethers called the Williamson ether synthesis.
Williamson.
Okay.
How does that work?
It's usually two steps. First, you react the alcohol with a strong base, often sodium metal or sodium hydride, to rip off the proton from the OH group. This forms an alkoxide ion. The oxygen now has a negative charge.
Alcohol becomes negatively charged alkoxide.
Yep, and this alkoxide is a strong nucleophile. In step 2, you react it with a primary alkyl halide. The alkoxide attacks the carbon holding the halogen, kicks the halogen out.
A substitution reaction.
Exactly, an SN2 reaction typically. And voila, you've formed an ether, a molecule with an oxygen bridging two carbon groups, ROR.
Neat. Alcohol to alkoxide to ether. What about going back towards carbonyls, like the reverse of reduction?
Oxidation, yes. That's a major transformation. You can oxidize alcohols back into carbonyl compounds.
So the opposite direction.
Right. And again, we have reagents with different strengths for control. One is PCC, pyridinium chlorochromate.
PCC, is that a pop gun or a cannon?
More like an oxidizing pop gun, maybe. It's a milder oxidizing agent.
Okay, what does PCC do?
If you use PCC on a primary alcohol, it oxidizes it cleanly to an aldehyde. It stops there.
Primary alcohol to aldehyde with PCC. Important, it stops there.
Yes. If you use PCC on a secondary alcohol, it oxidizes it to a ketone.
Secondary alcohol to ketone.
Now, if you want more power, you use something like the Jones reagent. That's often chromium trioxide, CrO3, mixed with acid and water. That's the stronger oxidizing agent.
The Jones reagent. The cannon?
Kind of, yeah. If you use the Jones reagent on a primary alcohol, it doesn't stop at the aldehyde. It keeps going and oxidizes it all the way to a carboxylic acid.
Okay. Primary alcohol to carboxylic acid with Jones. Big difference.
Huge difference. But if you use the Jones reagent on a secondary alcohol, it still just gives you a ketone, same as PCC.
Secondary alcohol to ketone with Jones, too.
And just like with reduction having a limit, there's a limit here, too. Tertiary alcohols.
Let me guess. They can't be oxidized.
You got it. Tertiary alcohols generally don't oxidize under these conditions because the carbon holding the OH group doesn't have a hydrogen atom attached to it, which is needed for these oxidation reactions to proceed.
No H on that carbon, no oxidation. Makes sense.
So again, the choice of reagent, PCC versus Jones, is critical, especially for primary alcohols, as it determines whether you get an aldehyde or a carboxylic acid. Control is everything.
Wow. So much you can do with alcohols and alcohols. We've covered a ton today in this deep dive.
We really have.
From just understanding the classification primary, secondary, tertiary, which predicts their behavior, to figuring out that systematic naming convention.
Yeah, IUPAC rules, yeah.
And then exploring all these amazing reactions, adding water to double bonds, reduction with pop guns and cannons, the Grignard for building things up.
8 synthesis tools.
And then transforming alcohols, dehydration to alkenes, Williamson for ethers, and oxidation back to aldehydes, ketones, or acids. It really shows how central they are.
They absolutely are, both starting materials and products, connecting huge parts of organic chemistry, and obviously relevant in so many products we use.
Definitely brings that organic chemistry for dummies chapter to life. It's less intimidating when you break it down like this.
I think that's the goal, right? To see the logic and the patterns.
So maybe a final thought for our listeners to chew on.
Well, considering all these ways alcohols can be made, and especially all the ways they can be transformed into other things with such specific control, what does that really tell us about maybe the sheer elegance and complexity of chemical synthesis? Both how nature does it and how chemists try to mimic or improve on that in the lab or in industry.
That is a deep thought.
Yeah.
The interconnectedness of it all, something to definitely mull over next time you use hand sanitizer or check your antifreeze.
Indeed.
Well, thank you so much for joining us on this deep dive into the world of alcohols. We hope you found it useful. Keep exploring, keep asking questions, and keep that curiosity burning.